There are quite a few laws that applies to very specific cases, and there are quite a few more that applies pretty much everywhere. And one of that is your universal law of gravity. So what it tells us, let me actually go to the explanation. If I have any object, right, it doesn't matter what it is, where it is, it doesn't matter. Say this can be a pencil in front of you, and they say this can represent a table, right? Your pencil has mass. Does it have mass? It has, right? Does your table have mass? That also has. And there will be certain distance between their centers. So universal law of gravity tells that the force with which they pull each other is directly proportional to the product of their mass and inversely proportional to the square of the distance. And when we combine them, obviously, I can rewrite this as the following relationship. And so we have the force to be equal to the proportionality constant m1 m2 divided by r square. This very formula is your universal law of gravity. That's it. Okay, so let's read through. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses, right? Inversely proportional to the square of the distance between them. So the explanation is that let the mass be m1, m2 and so on and so forth. So we end up with this particular formula. Now, there are certain properties that we have to be very clear with. So all this you guys know. Now this is quite simple. So we need to look at certain properties. So what are those properties? We have two objects which have mass m1 and m2, for example. And their center is somewhere over here and over here. This is a line connecting their centers. Sorry. This is a line connecting their centers. Now, it is always attractive. That is, this box will pull this mass. So this is always attractive. So it's an attractive force. So gravity is always an attractive force. It doesn't repel. First thing, it acts between any two masses. Again, here I've given a very hypothetical situation. So we have two objects on the surface of Mars. And that's Earth, by the way. So it can be anywhere and it can be negligible. You know, Mars itself has huge mass, right? And these two masses are nothing. But even then, these two masses will attract each other. It's a universal force. It's not only that we are just observing this behavior on the surface of the Earth, but it is so on any other surface. So that's Earth, by the way. And this point shows that it is applicable universally. So that's why I made this object on the surface of Mars, actually, universal force. Right? It's a long range force. So it's not only that this mass is attracting this particular heavy thing, but it can also attract Earth. Of course, it's a very small force, but it still can attract. Mars is attracting Earth. Earth is attracting Mars as well. So it's a long range force. So even Earth can feel the pull of this rock, technically. I too can feel the pull. It's always a pull force. So this is long range. This shows that it's long range. But it follows inverse square law. I too feel the pull, but it's very minute. Technically, it's very, very minute. Very small. Okay, I think you guys can't read that. It's very small. the pull is very small. It's weak basically. The reason being it follows something called as inverse square law. So when it comes to field, you guys have to be very thorough with this law. So let me explain this. See, inverse square law, it is applicable to light intensity, it is applicable to smell also, literally. Say if you have a perfume, and you spray it. Oh, actually I do have this. Just a second. If I spray it, so the intensity of smell over here compared to a meter away will reduce by a factor of 1 by r square. Say this intensity is I, that's the smell. And here the intensity will be smell by, say this is 1 meter away, or so this doesn't look like 1 meter. Say half a meter or 1/4 of a meter, 0.25 meter, and say this is 1.25 meter, right? So the intensity of the smell will be reduced by the square of the distance. So this will be 1 by 1.25 the whole square. And here it will be 1 by 0.25 the whole square. So if I do the math, let me do the math. 1 divided by 0.25 square is equal to 16. So this is proportional to 16 times, while we have at the other end 1 divided by 1.25 square. So this is 0.64. 0.64. So here the factor is 16 and here the factor is 0.64, just a meter away. So that's why it's called as inverse square law, because you have to square with the distance. Okay guys, that is your inverse square law. Next is, it is a central force. So you can see the centers are pulling. So this is a central force. And I think I have 3 more. It is a conservative force. That is, the work depends on the final and the initial position, not on the path. So basically it is a straight line. So since this is straight line, so this is the main feature of conservative force. So what is this? This is a container. The container came from Earth. It doesn't matter that it took many paths, right? It took many paths, but what matters is that finally it's over there. That's all it matters. So this is a conservative force. It's a weak force, obviously. It's the weakest of so because this of inverse square law, it is the weakest force amongst the 4 fundamental forces, right? Weakest force because of this factor, inverse square law, and it is independent of the medium. So here there is literally, this is vacuum actually. So it is the pull, right? This rock is pulling Earth also. So it is independent of, let me change the color. It's independent of medium. Okay, so I think I summarized all of it. Let's check. Yeah. So main features, it's always attractive. It acts between any 2 masses. It is a universal force. It's a long range force. It follows inverse square law. It's a central force. Okay. It's a conservative force. It is the weakest of the 4 fundamental forces, and the independence of the medium. Okay. So yeah, you can copy all of this